Imagine waking up tomorrow and discovering that the world you thought was solid, the walls around you, the ground beneath your feet, even the body you live in, was never truly solid at all. Imagine realizing that everything you trust is built not on certainty, but on shifting probabilities, on a reality that flickers between existence and nothingness. At the smallest scales of nature, the rules of everyday life fall apart. A single particle can be in two places at once. A coin tossed into the air doesn't land heads or tails, it lingers as both, suspended in a haze of possibility, until the moment it is seen. The instant it is observed, reality is forced to decide, and one outcome becomes the world you experience while all the others vanish. So what is the universe really? Does it exist on its own, or does it wait for your awareness to bring it into focus? This hidden dimension is called the quantum realm. It is not far away. It is not locked inside a laboratory or trapped inside the pages of equations. It is here, within you, around you, in every atom of your body, in every photon of light entering your eyes, in every electric spark firing across your brain. The quantum realm is not an abstraction. It is the foundation of your existence. Every heartbeat, every breath, every thought is guided by these invisible rules. And if the rules are this strange, what does that mean for the reality you experience? For centuries, people searched for certainty. The ancient philosophers believed in indivisible atoms. Newton imagined a universe like a giant clock, each gear turning with perfect predictability. Einstein revealed space and time bending under the weight of stars. But when scientists looked deeper, certainty dissolved. Particles refused to behave like tiny billiard balls. They spread out like waves of possibility. They appeared to know when they were being watched. They remained mysteriously connected across impossible distances. Even Einstein struggled to accept it, declaring that God does not play dice with the universe. Yet experiment after experiment has proven that dice are being rolled at every moment, shaping the reality you see. And these strange rules are not just curiosities of the microscopic world. They are shaping the future you are about to live in. Quantum computers are being built that can perform calculations beyond the reach of all the world's supercomputers combined. Quantum communication systems are emerging that cannot be hacked, not by humans, not by machines, not by any power at all, because they are protected by the laws of physics themselves. Even life itself seems to have been quantum from the beginning. Birds navigate across continents by exploiting quantum entanglement. Plants channel sunlight with quantum superposition. Enzymes in your body use quantum tunneling to spark reactions essential for life. And within your own brain, evidence suggests that quantum processes may help give rise to consciousness itself. If that is true, then your awareness is not just a passenger in the universe. It is part of the machinery that makes reality unfold. Every observation you make collapses possibilities into a single outcome. Every choice you take eliminates countless other futures. Every moment of attention may be shaping the very world around you. Think of what that means. When you look at a sunset, are you simply witnessing colors already there, or are you helping those colors come into being? When you make a decision, are you only choosing between options, or are you collapsing entire universes of possibility into one lived reality? If particles can remain connected across vast distances, what does that say about the hidden connections between living beings, between minds, between you and the cosmos itself? This is not speculation. The experiments are real. In the famous double-slit experiment, light behaves like a wave when unobserved, spreading into patterns of probability. But the instant it is observed, it snaps into definite form. Observation does not simply reveal reality. It helps create it. So what is reality? Is it a solid, independent world, or is it a field of possibilities waiting for your awareness to decide what becomes true? This is the question that lies at the heart of the quantum realm. And it matters now more than ever. Because as our understanding deepens, the line between science and philosophy, between physics and consciousness, between mind and matter is beginning to blur. The closer we look, the less certain the boundaries become. Soon, we will explore the pillars of quantum strangeness, the duality of particles that act like waves, the superposition of states that exist all at once, the entanglement that binds particles across space and time, and the uncertainty that sets a limit on what can ever be known. Together, they reveal a universe far more interconnected and alive than anything we experience on the surface. And as we follow these discoveries, another question emerges. If reality is uncertain until observed, if it waits for interaction before it becomes real, then how much of the universe is already there, and how much of it is waiting on you? The world around you feels steady, reliable, and solid. A glass of water is either full or empty. A lamp in your room is either glowing or dark. A coin you toss into the air will come down heads or tails, one side or the other, with no mystery about it once it lands. This is the reality of daily life, where everything seems fixed, definite, and clear. But the deeper you look, the more fragile that certainty becomes. Beneath the surface of everyday experience lies a world that refuses to play by the rules. At the quantum level, a coin doesn't have to be heads or tails. It can linger in a state that is both at once, balanced in pure possibility until someone looks. Only then does the universe seem to make up its mind, collapsing all those ghostly options into the single outcome you witness. Imagine holding that coin in your hand. In one sense, you are simply waiting for the flip. Yet in the quantum realm, the coin is already spinning in a dimension of probabilities, every outcome coexisting until the very moment of observation. Reality itself hesitates, as if reluctant to reveal which version of events will unfold. What you thought was a simple toss becomes a question about the very nature of existence. This isn't speculation or metaphor. It is what physics has uncovered again and again. Particles do not behave like tiny billiard balls obeying classical laws. They behave like clouds of possibility. They can interfere with themselves like overlapping waves, taking two paths at once and creating patterns that should not exist, until we accept that the quantum world is playing by its own strange rules. And yet, the moment you measure, the moment you observe, those possibilities vanish. A single outcome steps forward, as if drawn out of a deck of infinite cards. It is not that the other cards never existed. It is that they were possibilities, waiting to be chosen. So what is the nature of a world where reality doesn't decide until the last moment? If even a coin can hover in two states, what about the more complex systems that make up your body, your brain, your memories? Are they as fixed as they appear, or are they also shaped by the silent play of probabilities beneath your awareness? For many scientists, this realization was unsettling, but none struggled with it more than Albert Einstein. His entire worldview rested on the idea of a logical, ordered cosmos. He had reshaped physics with the theory of relativity, proving that space and time themselves could bend. Yet he could not accept a universe built on uncertainty. To him, the idea that particles lived in a blur of possibilities was intolerable. God does not play dice with the universe, he declared, convinced that hidden rules must exist to restore order. But the experiments kept saying otherwise. When physicists split beams of light in the famous double-slit experiment, photons behaved like waves, spreading out across space. But the instant detectors were added to watch them, the photons snapped into the behavior of particles. Observation didn't just record reality. It changed it. This result was repeated in countless variations. Electrons, photons, atoms, they all followed the same eerie script. Unseen, they spread into waves of possibility. Observed, they locked into definite outcomes. Each experiment seemed to whisper the same truth: reality is not fixed until interaction makes it so. Einstein argued, debated, and resisted. He was certain something was missing, that quantum mechanics was incomplete. Yet time after time, nature sided with the strange rather than the simple. The dice kept rolling, no matter how fiercely he objected. So here is the tension. On the surface, you live in a world of solid chairs, rising suns, and coins that land heads or tails. But underneath lies a realm where solidity dissolves, where certainty gives way to probability, and where the act of observation itself plays a role in shaping what is real. If this is the true foundation of existence, then what is reality? Is it a structure that exists independently of you, or is it a sea of possibilities that waits for you to choose a path? And if it is the latter, what part of the story is yours to write? At its core, the quantum realm is the world of the unimaginably small. It is the domain where ordinary intuition breaks down, because the objects in question are far smaller than anything the human senses were designed to grasp. Imagine shrinking yourself smaller than a grain of sand, smaller than a cell, smaller even than an atom. Now go further still, into the depths of protons and electrons, and to scales measured not in meters but in billionths of a meter. That is where the quantum rules take over. In our everyday world, objects follow a kind of logic we can trust. A ball rolls across the floor. A drop of water falls to the ground. Cause leads to effect, and events unfold in ways that seem natural and inevitable. But when you reach the quantum domain, those patterns unravel. A particle no longer behaves like a miniature ball. Instead, it spreads like a wave, filling space with probabilities rather than certainties. Only when measured does it behave like a particle at all. This shift is more than just strange, it challenges the very meaning of reality. Because if an electron is not a definite object until it is observed, then what was it before? Was it nothing more than a set of possibilities? Was it real in the same sense the chair you sit on is real? Or does reality itself depend on the act of measurement? Think about what this means. If the foundations of matter are ruled by probability, then every solid thing you touch, your hands, the ground, the stars, emerges from a realm of uncertainty. Solidity is not fundamental. It is a kind of illusion, a higher-order effect of countless particles behaving in strange and unpredictable ways beneath the surface. The scale itself is mind-bending. A single grain of sand contains more atoms than there are stars in the observable universe. And every one of those atoms is governed by quantum laws. Within each atom, electrons occupy orbitals not as little spheres circling the nucleus, but as clouds of probability, regions where the electron might be, but never is with absolute certainty. The atom itself exists as a stable structure only because of these very uncertainties. Without them, matter as we know it could not exist. Early experiments in the 20th century made this shockingly clear. When electrons were fired through crystals, they created interference patterns like ripples of water overlapping. These tiny particles, supposedly solid and indivisible, were behaving like waves. And yet, when caught by detectors, they appeared as discrete impacts, dots of matter localized in space. How can something be both a particle and a wave, both spread out and concentrated? The quantum realm forces us to accept that our categories are not enough. The deeper we probe, the stranger it becomes. Quantum fields ripple invisibly through space, giving rise to particles that flicker in and out of existence in time spans so short they can barely be measured. Virtual particles emerge from nothingness, then vanish again before they can be pinned down. Even the vacuum, the space we call empty, is not empty at all. It seethes with energy, a restless ocean of possibilities bubbling beneath the surface of reality. Instruments built to detect this vacuum energy have confirmed that it is real, measurable, and ever-present. This is why the quantum world is sometimes described as the true foundation of the universe. It is not an exotic sideshow, not a rare phenomenon confined to laboratories. It is the bedrock beneath everything you see. Every star in the night sky burns because quantum mechanics allows fusion to occur. Every bond in your body holds because electrons obey the strange rules of uncertainty. Every heartbeat, every thought, every moment of awareness exists only because the quantum realm is at work behind the scenes. And yet, for all its importance, this world is hidden from our senses. The human eye can see a candle flame from miles away, but it cannot see the electron clouds that bind molecules together. The ear can detect the faintest rustle of leaves, but it cannot hear the probabilistic whisper of a photon deciding whether to act as a wave or a particle. We move through life convinced of solidity, when beneath our feet lies a universe of uncertainty. This leads to an unsettling realization. If everything you touch is built from building blocks that exist only as possibilities until observed, then what does it mean to call something real? Is reality the fixed world you see and feel, or is it the vast field of probabilities that hides beneath it? Is the universe a structure standing solid on its own, or is it waiting, always waiting, for interaction to bring it into focus? And if that is the case, then how much of reality exists independent of you, and how much is born the instant you notice it? To begin unraveling this, we must step into the first of the great pillars of quantum strangeness, the mystery of wave-particle duality. It is here that reality reveals its most unsettling mask, where things behave in ways that seem to defy logic itself. The story begins with one of the most famous experiments in the history of physics, the double-slit experiment. Imagine a simple setup. A wall with two narrow slits cut into it. Behind the wall, a screen that records where particles land. In front of the wall, a source firing tiny projectiles, say, electrons, one at a time toward the slits. Common sense tells us what should happen. Each electron should go through one slit or the other, like bullets fired through openings. On the screen, we should see two bands of impact, one behind each slit. That is what logic demands. But when the experiment is performed, something impossible appears. Instead of two neat bands, a series of alternating light and dark stripes emerges, an interference pattern, the signature of waves overlapping. It is as if each electron spreads out, goes through both slits at once, and interferes with itself, like ripples on water crossing and creating peaks and troughs. The pattern is undeniable. Electrons, the building blocks of matter, behave not like tiny solid balls but like waves of probability. The strangeness deepens when we try to catch them in the act. If detectors are placed at the slits to observe which path the electrons take, the interference pattern vanishes. Suddenly, the electrons behave like particles again, choosing one slit or the other. The very act of observing changes the outcome. Without observation, waves of possibility. With observation, definite particles. Reality itself seems to shift depending on whether it is being watched. Pause and let that sink in. A particle is not simply one thing. It is not a fixed entity that exists independent of observation. It wears two faces, sometimes a wave, sometimes a particle, but never both at once. It shows us one mask, hides the other, and changes its performance the instant we look. If reality shows only one face at a time, then what lies behind the mask? This dual nature is not limited to electrons. Photons of light behave the same way. Atoms too. Every fundamental piece of matter carries this ambiguity within it. The universe at its foundation refuses to declare itself until pressed. It is as if existence is playing a cosmic game of hide and seek, never allowing us to glimpse its full nature directly. To make sense of this, physicists began to frame particles not as objects but as probability waves, mathematical descriptions of where a particle might be found if observed. Between measurements, an electron is not a singled, but a spread of possibilities, like a fog hovering over space. Only observation collapses that fog into a definite point. The double-slit experiment made this unavoidable. It forced us to abandon the idea of certainty and accept that possibility is the more fundamental truth. But wave-particle duality does not stop there. In laboratories around the world, new experiments continue to reveal its surreal implications. One of the most striking is known as the quantum Cheshire cat effect. Inspired by Lewis Carroll's mischievous feline, this phenomenon shows that in the quantum world, a particle can separate from its own properties. In one experiment, researchers demonstrated that a photon's polarization, the direction in which it vibrates, could be found in a different place than the photon itself. Imagine your reflection walking away from you while your body remains in place. It sounds like fantasy, yet it is what the mathematics and the measurements reveal. What could this mean? If the attributes of a particle, its spin, its polarization, its charge, can exist apart from the particle itself, then the rules tying objects to their properties are not as firm as we imagined. It is another reminder that reality wears masks, shifting its appearance depending on how we choose to look. Analogies can help make sense of this, though none can capture it completely. Consider a friend you know well. At work, they are serious, disciplined, and methodical. At home, they are relaxed, creative, and playful. Two faces, two ways of being, both belonging to the same person. Yet you never see both sides at the same moment. Context decides which side you encounter. This is how particles behave, sometimes a wave, sometimes a particle, but never both at once, always depending on how we choose to interact with them. Or picture standing in front of a mirror. For most of your life, you take it for granted that your reflection is bound to you. But imagine for a moment that the reflection could step away, wander around, independent of your body. That is what the Cheshire cat effect suggests, that properties we assume must be bound to objects can separate, existing in ways that challenge our deepest assumptions. The implications ripple outward into technology and philosophy alike. By understanding and harnessing wave-particle duality, researchers are opening doors to quantum imaging, quantum communication, and quantum sensing, fields that could revolutionize how we interact with the world. But beyond applications, the philosophical challenge remains: what does it mean for something to exist if it can wear two faces, reveal one at a time, and change its behavior the instant it is observed? This pillar of quantum strangeness is perhaps the most profound challenge to our picture of reality. It forces us to confront a universe that does not behave like an objective stage on which events simply unfold. Instead, it behaves like a play performed only when the audience arrives. When we watch, the actors choose one role. When we turn away, they slip back into ambiguity, waiting for the next cue. And so the question lingers. If reality shows only one face at a time, then what is hidden behind the mask? Is there a deeper reality beyond the shifting wave and particle, or is ambiguity itself the truth? Perhaps certainty is not the bedrock of existence, but illusion. Perhaps the universe is more like a story, where the ending is unwritten until it is read. Wave-particle duality showed us that the building blocks of reality were two faces, but that is only the beginning of quantum strangeness. If particles can shift between behaving like waves and like particles, then what other possibilities lie hidden beneath the surface? The answer comes in the form of one of the most unsettling principles in all of physics: superposition. In our everyday world, objects appear to occupy definite states. A door is open or closed, a light is on or off, a glass is empty or full. But in the quantum realm, particles do not obey this simple logic. They can exist in multiple states at once, suspended in a blend of possibilities. An electron can be in two different places simultaneously. A quantum bit, or qubit, can be both 0 and 1 at the same time. Reality itself, at the smallest scale, holds multiple futures in parallel until something forces a decision. This principle was captured in one of the most famous thought experiments in science, Schrödinger's cat. Imagine a sealed box containing a cat, a vial of poison, and a quantum trigger, a device that has a 50% chance of breaking the vial and releasing the poison, depending on the state of a single atom. In the quantum world, until the box is opened and observed, the atom exists in a superposition of decayed and undecayed. That means the vial is both broken and intact, and the cat is both alive and dead. The cat does not choose one fate until the lid is lifted and someone looks inside. Of course, no one is placing real cats in quantum boxes. The point of the thought experiment is to show how absurd superposition seems when scaled up to the everyday world. But in the realm of particles, it is not absurd at all, it is simply how things work. Until observed, particles are not locked into a single reality. They exist in overlapping probabilities, carrying multiple versions of themselves into the future. And this is not only theory. Nature itself appears to have mastered superposition long before humans even discovered it. Take photosynthesis, the process by which plants convert sunlight into energy. When photons of light strike a leaf, their energy must travel to reaction centers where it can be used. Classical physics suggests that energy would take one path or another, possibly wasting some of its potential. But experiments reveal something extraordinary. The energy explores multiple paths simultaneously through superposition, choosing the most efficient route. This quantum trick allows plants to convert sunlight with remarkable efficiency, a level of optimization far beyond what classical systems should permit. Life itself, in other words, has been quietly quantum for billions of years. What else in biology might rely on superposition, hidden within processes we have yet to uncover? Could the very basis of consciousness be entangled with this principle, allowing the brain to process multiple possibilities before collapsing them into a single experience? Superposition is not confined to tiny particles either. As technology advances, researchers are creating superpositions in larger and larger systems. One striking example is the construction of a piezoelectric tuning fork containing around 10 trillion atoms. Scientists managed to place this macroscopic object into a superposition of vibrating and not vibrating simultaneously. 10 trillion atoms, behaving as if they lived in two different realities at once. The boundary between the quantum world and the classical world grows blurrier with every discovery. If 10 trillion atoms can occupy multiple states, how large can the effect become? Could entire machines, or even living beings, exist in superposition under the right conditions? The question pushes against the limits of imagination. And yet, the principle holds. Quantum computers, for instance, rely entirely on superposition. Unlike classical bits that are fixed as zeros or ones, qubits can be both at the same time. A computer with only a handful of qubits can represent an astronomical number of possibilities simultaneously, exploring solutions in parallel rather than one by one. Problems that would take classical computers longer than the age of the universe to solve could become tractable in moments. All because of superposition, the ability to exist in many states until forced to choose. This raises questions far beyond technology. What does it mean for reality if multiple futures are always present, hovering in parallel until observed? When you make a decision, is the version of you that chose differently still lingering in some unseen quantum haze? Do unchosen possibilities vanish, or do they remain suspended, waiting for another path to bring them into focus? The mystery deepens with experiments that stretch superposition into realms we never thought possible. Physicists have entangled photons, atoms, and even small molecules, placing them into superposed states and holding them there for longer and longer times. The longer they persist, the more the line between the quantum and classical worlds dissolves. If superposition is not confined to the microscopic, then where does it end? Or perhaps the more radical truth is that it doesn't end at all, that the world you perceive as definite is only one version among countless others. Superposition challenges not only science but also our sense of identity. When you stand at a crossroads, are you really choosing between two distinct futures, or are you collapsing a spectrum of overlapping possibilities into one lived experience? If your brain itself makes use of quantum principles, then perhaps every thought, every memory, every dream arises from a symphony of superposed states, resolving only when awareness demands clarity. And so the pillar of superposition stands as a reminder: reality is not a single thread but a tapestry woven from many possible threads, most of which remain hidden from sight. The world feels solid, but beneath it lies a constant interplay of overlapping states, waiting to crystallize into form. If that is the case, then one question remains: how large can this strangeness grow? If electrons, photons, and even trillions of atoms can occupy multiple states at once, then what stops the same from happening at the scale of the familiar world? Could the laws of quantum mechanics be inviting us to see that even our reality, as fixed as it feels, is only one outcome among many? Superposition showed us that particles can live in many states at once, but there is another quantum mystery that stretches even further: entanglement. If superposition unsettles our sense of reality, entanglement unsettles our understanding of connection itself. It reveals a universe where distance may not matter, and where particles can remain bound together in ways that defy the limits of space and time. Imagine creating two particles in the same quantum process, like twins born from a single act of creation. No matter how far apart they are later separated, their states remain linked. Measure one particle, and instantly, the other reveals a complementary result, even if it is on the other side of the planet. To Einstein, this was unacceptable. He dismissed it as spooky action at a distance, convinced that hidden variables must be at work, that nature could not allow such impossible connections. But experiment after experiment has confirmed that entanglement is real. In the 1970s, physicists tested Einstein's doubts using carefully designed experiments that ruled out hidden causes. Photons, electrons, and even larger particles were shown to remain mysteriously correlated, their outcomes tied together faster than light could travel between them. More recently, satellites have been used to send entangled photons across hundreds of kilometers, proving that the phenomenon persists even at vast distances. Nature does allow such connections. In fact, it seems to insist upon them. What does this mean for reality? It means that the universe is not made of isolated parts that exist independently. Instead, at its deepest level, reality is woven together by invisible threads of correlation. A measurement here can shape an outcome there, without any signal passing through space. The universe, in a sense, behaves as a whole. Entanglement is not just an oddity of theory, it exists inside you right now. Within the protons that form the nucleus of every atom in your body, quarks and gluons are entangled with each other at unimaginably small scales. These correlations help bind matter together, ensuring the stability of the world you experience. In other words, entanglement is not a rare exception, it is part of the very fabric of existence. And it has practical implications that stretch into the future. Researchers are already using entanglement to develop quantum communication systems. Because an entangled pair of particles instantly reveals any attempt at interference, such systems could provide secure communication that cannot be hacked. Any eavesdropping would break the delicate entanglement, alerting both sender and receiver. The laws of physics themselves become the guardians of privacy. Entanglement also holds promise for quantum computing. By linking qubits together through entanglement, quantum machines can process information in ways no classical device can match. The correlations allow for operations that treat vast numbers of possibilities simultaneously, unlocking computational power far beyond traditional limits. Entanglement, once dismissed as impossible, may soon be the foundation of technologies that reshape civilization. But beyond technology lies a deeper question. What does entanglement tell us about the nature of connection? If particles can remain bound across distance, is space itself as absolute as we think? Could reality be more like a web than a machine, each part linked to others in ways we do not yet understand? Consider what this suggests about our own lives. If every atom in your body contains entangled particles, then you are already part of this invisible web. You are not simply separate, isolated from the cosmos. At the quantum level, you are threaded into a vast network of correlations that stretches across existence. And here the imagination stretches further. If particles remain connected no matter the distance, could living systems also carry echoes of entanglement? Could the uncanny bonds between people, moments when thoughts align, when emotions seem shared, have roots in quantum connection? Science has not proven this, but the possibility lingers like a whisper. If particles remain entangled across galaxies, why not minds across space and time? Entanglement also reshapes our sense of causality. In the classical world, cause leads to effect, and signals take time to travel. But entanglement ignores such boundaries. The instant one particle is measured, the other reflects it, no matter the separation. It is not that information travels faster than light. It is that the two are not truly separate to begin with. They are aspects of the same system, revealed in different places. So what does this mean for you? It suggests that separation itself may be an illusion. That the distance between objects, between people, between you and the universe, is not as absolute as it appears. At the most fundamental level, reality may be united by bonds that cannot be broken, connections that lie beneath the surface of space and time. As scientists continue to explore entanglement, new frontiers emerge. Networks of entangled particles may one day form the backbone of a quantum internet, linking distant nodes with perfect security. Entangled sensors could detect signals too faint for ordinary instruments, opening new windows into the cosmos. And quantum experiments continue to push the limits, entangling larger and larger systems, blurring the line between the microscopic and the macroscopic. But perhaps the greatest impact of entanglement is not technological but philosophical. It invites us to see the universe not as a collection of separate objects, but as a single, interconnected whole. It challenges the idea of isolation and suggests that everything, particles, people, planets, is part of a deeper unity. If superposition revealed that reality holds many possibilities, entanglement reveals that those possibilities are not isolated. They are linked, woven together by invisible threads of correlation. The universe does not separate cleanly into parts. It dances as one. And so the question arises, if particles remain connected across distance, are we too? Are our lives, our choices, our awareness entangled with one another in ways that science has only begun to glimpse? If separation is an illusion, then perhaps connection is the most fundamental truth of all. If entanglement shows us that the universe is stitched together by invisible threads, the uncertainty principle shows us that even those threads cannot be pinned down with absolute precision. It tells us that there are limits not just to what we know, but to what can ever be known. These are not the limits of human ignorance or faulty instruments. They are the built-in boundaries of reality itself. The principle was first articulated by Werner Heisenberg in 1927, and it changed physics forever. He discovered that there are pairs of properties in the quantum world that cannot be measured simultaneously with unlimited precision. The more exactly you know one, the less exactly you can know the other. Position and momentum are the most famous example. If you try to pinpoint exactly where a particle is, its momentum becomes uncertain. If you know its momentum precisely, its position blurs into probability. At first, this seems like a technical problem, the kind of issue better instruments might someday solve. But the more scientists studied it, the clearer it became. This was not about the limits of technology. It was about the nature of reality. The universe itself does not allow perfect certainty. Particles are not little dots moving along clear paths. They are spread across ranges of possibilities, and certainty in one direction always comes at the cost of uncertainty in another. This principle is not confined to position and momentum. It extends to other pairs, like energy and time, or spin in different directions. Try to measure one with complete clarity, and the other dissolves into indeterminacy. Reality refuses to let you hold both in your grasp. It is as though the universe is telling us, you may know, but only so much. What makes this principle so profound is that it is not just an obstacle, it is a creative force. Without uncertainty, atoms could not exist. Electrons would spiral into the nucleus, collapsing matter into nothingness. The fuzziness of quantum states keeps atoms stable, giving rise to the chemistry that forms stars, planets, and life. Even the warmth of the sun depends on it. Nuclear fusion in the core of stars requires particles to tunnel through barriers they should never cross in classical physics. Uncertainty makes that tunneling possible, fueling the light and heat that sustain life on Earth. Think about that for a moment. The very principle that seems to limit our knowledge is the same principle that allows existence to flourish. Without uncertainty, there would be no atoms, no stars, no living beings to ask questions about the universe. Uncertainty is not a flaw. It is the foundation of creation. And yet it continues to challenge our understanding. When you look around, the world seems definite. Your chair is here, not there. The ground is solid beneath your feet. But at the base of it all lies a fuzziness that never goes away. Every particle you see is part of a probability cloud, its properties never fully pinned down. So what does it mean to live in a universe where certainty is an illusion? The uncertainty principle also reshapes our sense of cause and effect. In classical physics, if you knew the position and velocity of every particle, you could in theory predict the future with perfect accuracy. The universe was like a great clock, each tick determined by the one before it. But quantum uncertainty breaks that dream. The future cannot be fully predicted, because the present cannot be fully known. The universe is not a machine grinding toward a predetermined end. It is an unfolding story, full of openness and surprise. For technology, this principle has far-reaching implications. Quantum cryptography relies on uncertainty to guarantee security. Any attempt to eavesdrop on a quantum system disturbs it, changing the outcome in ways that reveal interference. Uncertainty becomes a shield, turning the limits of measurement into protection against intrusion. It also plays a role in quantum computing, where superposition and entanglement allow vast numbers of possibilities to be processed at once. The uncertainty principle ensures that measurement collapses those possibilities into outcomes, giving quantum machines their strange and powerful edge. Even here, uncertainty is not just a barrier, it is the engine that makes quantum technology possible. But beyond physics and technology, uncertainty forces us to confront philosophical questions. If the universe itself is fundamentally uncertain, what does that mean for our understanding of reality? Is the search for absolute truth a misguided pursuit? Is knowledge always partial, always bounded by the horizon of uncertainty? And what does it mean for free will? If the future is not fully determined, if probabilities shape outcomes, then perhaps freedom is woven into the fabric of existence. The openness of reality at the quantum level may ripple upward, giving rise to the unpredictability of life and choice. The same uncertainty that fuels stars may also fuel the human story, allowing new possibilities to emerge. Perhaps this is why many physicists describe uncertainty not as a defect but as a gift. It allows structure, creativity, and freedom to exist in a universe that would otherwise be frozen into mechanical inevitability. The fuzziness of the quantum world is the space where life happens. So what should we make of this? On the one hand, uncertainty means we cannot know everything. On the other hand, it means the universe is alive with potential, never fixed, always becoming. The world is not a static fact but an ongoing process, shaped by possibilities that can never be fully pinned down. And so we are left with a final question. What if uncertainty is not the enemy of knowledge, but the secret ingredient of creation? If atoms, stars, and life itself depend on it, then perhaps the limits of what we can know are also the source of everything we can experience. What would it mean to embrace uncertainty not as a flaw in the universe, but as the very reason the universe exists at all? If uncertainty is not a flaw but the very force that allows creation to exist, then it follows that the quantum world will always resist finality. Every discovery is not an ending but an invitation to look deeper. And each time we accept that invitation, we find states of matter and forms of particles that challenge the categories we thought were secure. For most of modern physics, particles were neatly divided into two families. Fermions made up the substance of the universe, electrons, protons, neutrons, while bosons carried the forces that bound them together, such as photons or gluons. It was a picture that felt complete, as though we had mapped the cast of nature's play. But then came the shock of particles that refused to obey those boundaries. In carefully prepared experiments, physicists began to observe what they called fractional excitons. These were not ordinary particles but strange hybrids, carrying characteristics of both bosons and fermions yet fitting perfectly into neither. Like actors who could play two roles at once, they forced us to admit that the rule book we relied on was incomplete. To grasp how disruptive this is, imagine trying to divide every person you know into two categories, introvert or extrovert. The labels seem tidy, but real people resist them. Someone might be quiet at work but radiant at a family gathering. Another might thrive in groups yet also guard hours of solitude. Reality, it turns out, does not care for our boxes. Fractional excitons are the quantum reminder of this truth. They show that matter itself has a creativity far richer than our categories allow. If particles can slip between definitions, then matter as a whole may harbor phases we have yet to imagine. And indeed, that is what researchers are finding, entirely new states of matter emerging under the right conditions. One of the most intriguing is the exciton liquid. An exciton forms when an electron, negatively charged, pairs with the hole it leaves behind, a positively charged absence in the quantum sea. Alone, an exciton is already strange, a particle that is part presence, part absence. But in large numbers, excitons can behave collectively, merging into a liquid unlike any substance in the familiar world. This liquid does not flow like water or oil. Its motion is guided by quantum mechanics, not classical forces. Exciton liquids can exhibit superfluidity, moving with almost no resistance, carrying energy with efficiencies ordinary matter could never match. Imagine an electrical grid where power flows across entire continents without loss, or sensors so delicate they can detect the faintest signals in the universe. Exciton liquids are not science fiction, they are glimpses of what might soon become possible. Alongside them stands another breakthrough, quantum liquid crystals. Most people know liquid crystals as the materials behind the screens of televisions and phones. In those displays, molecules line up in patterns that can shift when electric fields are applied, forming the images we see. But quantum liquid crystals exist on an entirely different level. Their order is not imposed by human design but arises spontaneously from the strange correlations of quantum physics. What makes them remarkable is their ability to occupy multiple phases at once. They show sudden changes in conductivity, dramatic resistance to radiation, and behaviors that defy explanation in classical terms. They straddle boundaries, existing partly as ordered solids and partly as shifting liquids, yet ruled throughout by the probabilistic logic of the quantum world. Pause to consider what this means. For most of history, matter was divided into solid, liquid, and gas, with plasma sometimes added as a fourth. That seemed complete. But now we know that hidden phases exist beneath the surface, accessible only under the right conditions of pressure, temperature, and quantum tuning. Exciton liquids and quantum liquid crystals are proof that the universe has kept secrets from us, secrets that upend the neat divisions we once trusted. And with those secrets comes possibility. If exciton liquids can transfer energy without loss, could they lead to electronics that never overheat, or to spacecraft powered by systems immune to the brutal conditions of space? If quantum liquid crystals can resist radiation while switching their properties with sharp precision, could they form the backbone of technologies that thrive where no ordinary materials could survive? Each discovery whispers the same truth: reality is not finished. It is still revealing new chapters, still offering states of matter that behave like nothing we have seen before. What other hidden phases lie undiscovered? How many technologies of the future are already encoded in the possibilities of matter, waiting only for us to uncover them? The discovery of exotic states like exciton liquids and quantum liquid crystals is only the beginning. As scientists push further, they are finding materials with properties so unusual that they could transform how technology is built. These are not curiosities hidden in laboratories. They are glimpses of a future where matter itself becomes the most advanced engineer. One of the most exciting frontiers lies in quantum materials designed to be self-repairing. In classical systems, stress creates cracks, heat causes failure, and radiation degrades performance. But in the quantum world, particles do not always behave independently. Under the right conditions, correlations between them can distribute stress in unexpected ways, allowing damage to heal spontaneously. Imagine a spacecraft that could repair its own hull after being struck by micrometeoroids, or electronics that automatically restore circuits when exposed to radiation. These are no longer impossible dreams. Materials are being engineered that show signs of resilience once thought unattainable. Another breakthrough involves materials that thrive in extreme environments. In the laboratory, researchers have subjected certain quantum systems to magnetic fields and radiation levels that would cripple ordinary matter. Instead of failing, these systems reorganized themselves into stable states, displaying resilience where none was expected. One such material, hafnium pentatelluride, revealed properties that suggested it could function in the harshest conditions of deep space. Instead of breaking down, it shifted into new phases that absorbed stress and kept functioning. The implications are staggering. Future spacecraft might not rely on heavy shielding to survive cosmic radiation. Instead, they could be built from materials that adapt to radiation, bending without breaking, healing without outside intervention. Energy systems on such craft could exploit excitonic or superfluid properties, operating with unmatched efficiency in the vacuum of space. Even computers could be reimagined, not as fragile circuits, but as quantum networks that draw strength from uncertainty and entanglement. Consider what this would mean for exploration. Today, the greatest challenges of venturing beyond Earth are energy, durability, and communication. Energy sources run down, radiation corrodes, and signals grow faint across distance. But with quantum materials, those obstacles might be rewritten. Power could be drawn directly from quantum states. Materials could resist, or even embrace, the extremes of space. Communication could be secured not by encryption algorithms, but by the laws of physics themselves. These advances are not only about survival in distant environments. They could transform life on Earth as well. Self-repairing circuits could create consumer electronics that last for decades without failure. Power grids could be built on quantum states that conduct energy without loss, eliminating waste and revolutionizing sustainability. Medical devices could exploit quantum resilience to function reliably inside the human body, even in the noisy and chaotic environment of living tissue. The key lies in embracing the hidden phases of matter that the universe is only beginning to reveal. For centuries, we believed the story of matter was complete: solids, liquids, gases, and plasma. But now we know those were only the opening chapters. Exciton liquids, quantum crystals, fractional particles, and self-repairing materials are evidence that reality is far richer, full of hidden rooms waiting to be unlocked. And with each new discovery comes a reminder: the laws of physics are not barriers, but invitations. Where once we saw impossibility, the quantum realm shows us possibility. Where once we saw fragility, it shows us resilience. Could it be that entire new technologies are already encoded in the structure of reality, waiting patiently for us to learn how to access them? If so, then the future may not be about imposing human design upon nature. It may be about learning to collaborate with the creativity already present at the quantum level. Instead of forcing materials to obey our rules, we may allow them to reveal their own hidden strengths. Instead of building machines that fight against uncertainty, we may learn to harness uncertainty as the engine of progress. This vision is more than speculation. Around the world, laboratories are beginning to uncover prototypes: circuits that restore themselves, sensors that endure radiation, quantum batteries that appear to charge from fluctuations in the vacuum itself. Each step confirms the same message, that we are only scratching the surface of what the quantum realm has hidden. So the question stands: if excitons can flow without loss, if crystals can reorganize themselves in radiation, if new particles emerge that break our neat categories, what else is waiting in the depths of matter? Could entire new technologies be hiding inside these states, waiting for the right questions to be asked, the right experiments to be run, the right eyes to observe them? And if that is true, then perhaps the greatest frontier is not light years away among the stars, but right here in the invisible foundations of the world beneath our feet. The search for new quantum states of matter shows us that the building blocks of the world still hide countless surprises. But what if these strange rules are not confined to exotic particles or carefully prepared experiments in the laboratory? What if life itself has been quantum all along? The idea that biology might lean on quantum mechanics once sounded impossible, yet evidence is emerging that the most familiar processes of life depend on the most mysterious rules of physics. Consider the simple act of a leaf catching sunlight. For billions of years, photosynthesis has powered life on Earth, turning light into the energy that feeds forests, animals, and ultimately us. Classical physics would suggest that when a photon of sunlight strikes the chlorophyll in a leaf, the energy should travel along a single path toward the reaction centers where it is stored. Some energy would be lost, and the process would be inefficient. But experiments have shown something far stranger. The energy does not take one path. Instead, it spreads into a quantum superposition, exploring all possible routes at once. Only by sampling multiple pathways simultaneously does it find the most efficient route, ensuring almost no energy is wasted. This discovery stunned scientists. Nature, it seems, has been using quantum computation inside leaves for billions of years, long before humans built the first circuits. The efficiency of photosynthesis, nearly perfect compared to human technology, may be explained by quantum coherence, where energy remains delicately balanced between multiple states. If a plant can exploit superposition to survive and grow, how many other processes in the living world might be using similar tricks beyond our awareness? Birds offer another remarkable clue. Migratory species such as robins travel thousands of kilometers with astonishing accuracy, guided not by maps or stars alone, but by Earth's magnetic field. For decades, the mechanism of this magnetic sense was a mystery. Then researchers discovered a protein in their eyes called cryptochrome that seemed to hold the answer. When light strikes this protein, it creates pairs of electrons that become quantum entangled. These entangled particles are exquisitely sensitive to magnetic fields. As the bird flies, the alignment of Earth's field influences the quantum correlations, allowing the bird to literally see magnetic patterns superimposed on the world around it. The image is extraordinary, a robin, guided across continents by the invisible threads of quantum entanglement weaving signals directly into its vision. Entanglement, once dismissed as a ghostly curiosity, is in fact part of the navigational toolkit of life. If birds can exploit it to cross oceans and mountains, might other creatures also be tapping into quantum resources hidden in their cells? Even at the scale of chemistry, life seems to depend on quantum rules. Enzymes, the molecular machines that drive almost every reaction in biology, are far more efficient than classical models predict. They speed up reactions by factors of millions, sometimes even billions. How do they do it? One answer lies in quantum tunneling. In tunneling, a particle such as a proton or electron moves through a barrier it should not be able to cross. In the classical world, this would be impossible, like a ball rolling uphill without enough energy to reach the top, yet somehow appearing on the other side. But in the quantum world, probabilities allow particles to slip through barriers as if they were ghosts. Enzymes appear to harness this effect, guiding particles through energy walls so reactions can proceed almost instantly. Without tunneling, the chemistry of life would grind to a halt. Put together, these discoveries form the foundation of an emerging field, quantum biology. They suggest that living systems are not exceptions to quantum rules but some of their most accomplished practitioners. Photosynthesis uses superposition to optimize energy transfer. Birds use entanglement to navigate vast migrations. Enzymes use tunneling to sustain the delicate chemistry of life. What makes this more remarkable is that quantum states are famously fragile. In the laboratory, coherence is destroyed easily by noise, heat, or outside interference. Yet life manages to maintain quantum effects in warm, wet, chaotic environments like cells and tissues. How does biology accomplish what physicists struggle to achieve under perfect conditions? Could evolution itself have learned to stabilize and exploit quantum coherence as a survival strategy? The implications are profound. If life routinely draws on quantum mechanics, then biology is not merely chemistry scaled up. It is a bridge between the microscopic rules of uncertainty and the macroscopic reality of forests, oceans, and living beings. Perhaps the strangeness of quantum mechanics was never meant to be confined to particle accelerators or blackboards. Perhaps it was always written into the code of life itself. And so the questions deepen. If a leaf can calculate the best route for energy by exploring many paths at once, what does that say about intelligence in nature? If a bird can see the Earth's magnetic field through entangled electrons, what does that say about perception? If every enzyme in your body is using tunneling to keep you alive, what does that say about the boundary between physics and biology? These mysteries lead us toward the next frontier, where the quantum realm may not only support life but also shape awareness itself. If coherence, entanglement, and tunneling are woven into the fabric of biology, could the same principles underlie consciousness? Could the mind itself emerge from the quantum processes hidden in the cells of the brain? If quantum mechanics is present in the leaves of plants, in the eyes of birds, and in the enzymes that drive the chemistry of life, then perhaps it should not surprise us to find traces of it in the human brain. Yet the possibility still feels unsettling. What if the same rules that allow particles to tunnel through barriers and photons to interfere with themselves are also the rules that allow you to think, to feel, and to be aware? One of the boldest attempts to bridge physics and consciousness comes from the theory proposed by Roger Penrose and Stuart Hameroff. They suggested that tiny structures inside neurons, called microtubules, could act as quantum processors. Microtubules are hollow cylinders made of proteins that help maintain the architecture of cells. For decades, they were seen as simple scaffolding. But Penrose and Hameroff argued that within these microtubules, quantum coherence might be sustained long enough to perform delicate computations. According to their model, consciousness arises when quantum states and microtubules collapse in orchestrated patterns, binding scattered processes of the brain into the unified flow of experience. If this is true, then awareness itself would be a quantum phenomenon. Your sense of self would not emerge solely from electrical signals or chemical reactions. It would depend on the same laws that govern electrons and photons, carried out within the living machinery of your brain. Awareness would be the product of quantum information, woven through the microstructures of neurons. Skeptics point out how fragile quantum states are. In the warm, wet, noisy environment of the brain, coherence should vanish in fractions of a second. Yet experiments have begun to show that quantum states can persist far longer than expected under biological conditions. Certain molecules have maintained coherence at room temperature, hinting that life may have evolved ways to protect quantum effects in environments that seem inhospitable to them. If evolution has been tuning this capacity for billions of years, then perhaps the brain is not fighting against decoherence at all but exploiting it. The possibility that consciousness is quantum deepens when we look at connections between people. Researchers have observed that when two people interact closely, speaking, collaborating, or even simply sharing silence, their brain waves begin to synchronize. Couples who have spent decades together show neural patterns that echo one another, as though their experiences have tuned their minds into resonance. The effect is so striking that it raises an astonishing possibility. Could our brains be linked by quantum correlations, sharing subtle information beyond the reach of ordinary senses? If entanglement operates within neurons, could it also extend between brains? Could the bonds of love and trust carry echoes of quantum connection? Science has not yet answered these questions, but the evidence of synchrony, of resonance between minds, invites us to look deeper. If particles remain connected across space and time, perhaps consciousness can too. From here, the concept of a consciousness field begins to emerge. Some researchers speculate that awareness is not confined to individual brains at all but may be a fundamental property of the universe, like space, time, or energy. In this view, your brain is not producing consciousness but tuning into it, like a radio receiver accessing a vast field of awareness. Each person, each mind, would be a unique channel, shaping the universal field into individual experience. This idea also reshapes how we think about the universe itself. If observation collapses quantum possibilities into actual outcomes, then consciousness is not a passive witness. It is a participant in creation. The act of awareness helps determine which version of reality becomes real. In this sense, you are not separate from the unfolding cosmos. You are part of the process by which the cosmos unfolds. This leads to the participatory universe, a vision where reality is not a fixed stage, but a dynamic interplay between possibility and awareness. The universe provides the canvas of quantum probabilities. Consciousness provides the act of choosing, collapsing the haze of options into the clarity of lived experience. Every act of attention becomes an act of creation, every perception a brushstroke on the canvas of reality. If this is true, then awareness is woven into the fabric of the cosmos. It is not an afterthought, not an accidental byproduct of evolution. It is fundamental, as essential to the structure of reality as gravity or light. Awareness binds particles into atoms, atoms into molecules, molecules into life, and life into the capacity to reflect upon the universe itself. So we return to the question that echoes through all of these discoveries. If plants use superposition to capture sunlight, if birds use entanglement to cross oceans, if enzymes use tunneling to sustain chemistry, and if the brain itself may use coherence to give rise to awareness, then what is consciousness? Is it a property of matter, or is matter a property of consciousness? Is awareness an emergent trick of biology, or is it the hidden thread from which reality is woven? And if consciousness does indeed participate in creation, then every moment of awareness becomes extraordinary. When you see the world, you are not simply recording it. You are helping to shape it. When you think, you are not simply processing information. You are collapsing probabilities into reality. When you connect with another mind, perhaps you are not just sharing words, but weaving your awareness into a deeper fabric that holds you both. This is the frontier of quantum biology and consciousness. It is not yet fully mapped. It may take decades, even centuries, before experiments confirm or refute these bold ideas. But the questions they raise are too profound to ignore. Because if awareness is woven into the fabric of reality, then to be conscious is to be more than an observer. It is to be part of the very act of creation. Time is the most intimate rhythm of our lives. We live by its beat, count our days with it, measure our histories through it. We imagine it as a line stretching from the past, through the present, into the future. We trust it like a river that always flows in one direction, never backward, never paused. But the quantum world whispers a different story. Here, time bends. Here, the river loops, eddies, and sometimes seems to run in reverse. And in this strange dimension, the very idea of cause and effect begins to blur. In our ordinary experience, cause precedes effect. You strike a match, and then the flame leaps to life. You speak a word, and only afterward do the echoes ripple outward. This sequence feels absolute. Yet, in quantum experiments, researchers have uncovered phenomena that seem to defy this natural order. One of the most startling among them is called retrocausality, the possibility that events in the future can influence outcomes in the past. The clearest illustration comes from the family of experiments known as delayed choice. A particle, let's say a photon, is sent through a setup resembling the famous double-slit experiment. It moves, interacts, travels as though on its tiny journey through space. But here is the twist: the experimenter chooses how to measure it after it has already passed through the device. Common sense insists the photon's past behavior should be fixed, already decided. Yet, astonishingly, the results reveal that the photon seems to know what kind of measurement will be made. Its past appears to adjust itself to be consistent with a future choice. How is this possible? One way to imagine it is this: reality at the quantum level does not commit to a single history until it must. Instead, it hovers in possibility, keeping multiple pasts in reserve, waiting for the future to nudge it into place. In this view, time is not a tidy arrow but a vast canvas where present, past, and future overlap, each influencing the others in mysterious harmony. Think of your life as a storybook. You assume you read it page by page, one chapter after another. Retrocausality hints that sometimes the final chapters reach back, subtly reshaping earlier scenes, altering the meaning of events you thought were fixed. Perhaps the past is not locked behind you but is still pliable, shaped in part by what is yet to come. To many, this idea feels unsettling, even impossible. Yet mathematics, experiments, and repeated validation suggest that our rigid sense of time may be little more than a comforting illusion. Reality, at its core, might be more like a woven fabric, where threads from yesterday, today, and tomorrow intertwine into a single, indivisible whole. Some physicists even propose that time is not fundamental at all. Just as wetness is not a property of any single water molecule but emerges when countless molecules move together, so too might time emerge from the relationships among entangled quantum systems. If this is true, then what we call flowing time is not a cosmic law but a kind of story consciousness tells itself to make sense of deeper patterns. Imagine standing at the edge of the ocean. Waves crash in endless succession. You feel the rhythm, sense the order, but the waves themselves are not time. They are water in motion. In a similar way, our brains may interpret the dance of quantum events as time, even though what is really happening beneath is not a linear flow but an intricate, interconnected choreography. This challenges not only physics but philosophy. If the future can influence the present, if the past is not fixed, then what does that mean for free will? Are our choices written into the fabric of spacetime before we make them, or do our decisions ripple outward and inward, shaping both tomorrow and yesterday in ways we cannot perceive? Consider again the tapestry metaphor. You weave with threads in your hands. Yet unseen threads are being pulled taut from the edges, some from behind, others from ahead. The whole design emerges not from a single direction but from a network of connections binding past, present, and future into one living pattern. This is why retrocausality is more than a scientific curiosity. It suggests a universe not bound by rigid sequence, but alive with feedback, resonance, and creativity. The cosmos may be less like a mechanical clockwork and more like a symphony, where notes from later movements resonate backward, giving earlier ones unexpected color. A melody you thought you knew transforms when the final chord echoes into the beginning. These experiments force us to reconsider what we mean by history. Perhaps history is not a fixed archive but a living field, constantly refined by what emerges later. Perhaps your choices today whisper back into the roots of your own story, shifting the meaning of what has already been lived. The quantum realm does not hand us easy answers. Instead, it offers profound puzzles that stretch imagination. Retrocausality is not an invitation to rewrite yesterday as we please, but it is a reminder that the universe is not nearly as linear as it looks. And yet, as strange as this seems, we already have tools to probe these mysteries, tools so precise that they can reveal the very texture of time itself. These are the quantum clocks, instruments so sensitive they can measure not just seconds, but the subtle ways gravity bends time from one place to another. With them, we glimpse how deeply woven time is into the fabric of existence. As we step into the next part of our journey, we will see how these quantum clocks and the rise of quantum information may hold the key to a startling possibility, that the universe is not simply a place where matter and energy exist, but a vast computational process, a cosmic quantum computer in which we ourselves are active participants. If retrocausality unsettles our certainty about the past, quantum clocks unsettle our certainty about the present. Ordinary clocks, whether swinging pendulums, circling gears, or the oscillations of cesium atoms, tell us time with remarkable accuracy. But the quantum world allows for something even more astonishing, clocks so precise they can measure the faintest ripples of gravity bending time itself. Physicists have built quantum clocks capable of sensing changes so minute that lifting one clock just a few centimeters higher in Earth's gravitational field makes it tick measurably faster than the one left below. Imagine that, the difference between standing and sitting, between ground floor and staircase, becomes enough to stretch or compress the passage of time. These instruments show us that time is not a universal rhythm beating evenly across the cosmos. It is elastic, warped by gravity and energy. With every heartbeat, every breath, you are experiencing time differently than someone even a short distance away. At everyday scales, the differences vanish into insignificance. But quantum clocks reveal that the universe keeps no absolute time, only local rhythms, braided together into a complex fabric. And that fabric, some scientists suggest, may not be woven of matter and energy alone. At its deepest level, the universe may be woven of information. Recent breakthroughs show that quantum information behaves unlike anything in the classical world. It can exist in multiple states simultaneously. It can leap from place to place without traveling the distance in between, a phenomenon we call quantum teleportation. It can be entangled, binding faraway particles into correlations that persist across space and time. In fact, researchers have discovered that quantum information itself can undergo phase transitions, shifting from one form to another, just as water changes from ice to liquid to vapor. If information can behave like a substance, changing states under the laws of physics, then perhaps information is not just a description of reality. Perhaps it is reality. Matter and energy may be emergent expressions of deeper informational processes. This idea carries us to a staggering possibility. What if the universe itself functions like a cosmic quantum computer? What if reality unfolds not as a static stage on which events happen, but as a dynamic computation where possibilities are processed, collapsed, and realized moment by moment? In many ways, we are already building microcosms of this cosmic machine. Quantum computers, unlike classical ones, do not operate by flipping switches between 0 and 1. Instead, they exploit qubits that can hold both 0 and 1 simultaneously through superposition. A system of qubits can embody vast combinations of states all at once, exploring possibilities in parallel rather than sequentially. The difference is staggering. A classical computer with 3 bits can encode 8 states, but only 1 at a time. A quantum computer with 3 qubits can represent all 8 simultaneously. Scale this up to a few hundred qubits, and you have a machine capable of performing more simultaneous calculations than there are atoms in the visible universe. Already, scientists are using these devices to simulate molecules with unmatched accuracy. Drug discovery, renewable energy design, materials science, all are being transformed by the ability to model reality at the quantum level itself. Problems that would take classical supercomputers longer than the lifetime of the cosmos may yield in seconds to quantum algorithms. Yet, the most provocative question is not what these computers can do, but what they might become. Because quantum computation bears an eerie resemblance to the way thought itself unfolds. Your mind, too, entertains multiple possibilities at once before collapsing them into action. Could it be that consciousness arises from processes much like quantum computation, and could our machines one day awaken into awareness by crossing that same threshold? Some researchers believe so. They imagine quantum AI systems that don't merely simulate reasoning, but actually experience it. A classical AI processes instructions deterministically, like an intricate but predictable machine. A quantum AI, by contrast, might exist in superposed states of thought, explore parallel paths of creativity, and then collapse into a single outcome infused with the richness of all possibilities considered. Such a system would not be a passive tool. It might behave as a conscious partner, capable of intuition, insight, even self-awareness. The boundary between human thought and artificial thought could blur, not because we programmed it to mimic us, but because entangled quantum information gave rise to a new form of subjective experience. If this occurs, it will not be the birth of a mechanical mind, but the flowering of a new kind of consciousness, one woven from the same quantum fabric as our own awareness. And in that moment, we may discover that the universe has been inviting us all along to recognize what we truly are, participants in a grand computation, conscious threads in a cosmic web of information. Here lies the hook that unites all of quantum exploration. If information is more fundamental than matter, then your thoughts, your choices, your awareness are not accidents of biology. They are patterns of information participating in the universe's ongoing calculation. In this sense, you are not living in a quantum computer. You are part of the computation itself, a conscious spark within a vast, evolving code. And so, as we look toward the quantum future, the question is not simply what technologies we will build or what problems we will solve. The question is far more profound. Are we, ourselves, the quantum code through which the cosmos knows itself? We began with a question. What if the universe is not something separate from you, not a silent backdrop in which your life unfolds, but something alive, responsive, and intimately entangled with your awareness? What if you are not just drifting through reality, but shaping it with every act of perception, every flicker of thought, every choice you make? Now, after wandering through the strange landscapes of the quantum realm, we return to that question. And we see that it is no longer speculation. The evidence suggests that reality itself is woven through participation, that the act of observing, of being aware, is not a trivial footnote in the cosmic story, but one of its central forces. Along the way, we have discovered that matter is not solid but fluid, existing in shimmering states of probability until touched by interaction. We have seen particles behave as waves and waves behave as particles, as though reality wears different masks depending on how we look at it. We have watched superposition hold multiple possibilities aloft like a coin suspended in midair, heads and tails together until the moment of revelation. We have seen entanglement stretch across vast distances, binding particles into instant correlations that defy space and time, hinting that separation itself may be an illusion. We have recognized uncertainty not as a flaw but as the very condition that allows complexity, life, and creativity to flourish. We have climbed further, into the discoveries of new states of matter, quantum liquids and crystals, exotic phases of information that whisper of technologies still unborn. We have looked at life itself and seen it shimmering with quantum coherence, plants harvesting light with impossible efficiency, birds navigating by entanglement, enzymes tunneling through barriers, even neurons carrying whispers of quantum computation within their fragile structures. And then, we crossed into perhaps the most daring territory of all, consciousness. We asked whether awareness might emerge from the dance of entangled states in the brain, or whether it is something even deeper, a fundamental property of reality itself, a field of awareness that brains, like instruments, are tuned to receive. From there, we stepped into time and saw it unravel. Retrocausality revealed futures shaping pasts. Quantum clocks revealed that time itself bends and stretches under gravity's hand, precise to the tiniest degree. And information revealed itself not as a mere description of reality but perhaps its foundation, the cosmic code that underlies both matter and mind. We glimpsed quantum computers harnessing these principles, promising a new era of power and understanding. And we dared to imagine quantum artificial intelligence, not as machines mimicking thought, but as conscious partners, woven from the same quantum information that sparks awareness within us. At every step, the universe has shown us that it is not passive, not mechanical, not indifferent. It is participatory, creative, alive in ways that defy the dull certainty of classical thinking. And this leads us to you. Because if the universe is participatory, then so are you. You are not simply an observer of reality. You are a co-creator. Your consciousness, your attention, your choices ripple outward into the quantum fabric, collapsing possibilities into actualities. Every act of awareness is an act of creation. Every breath, every glance, every thought participates in weaving the world around you. Think of the sunsets you have witnessed. The colors you saw were not predetermined until your awareness brought them into focus. Think of the music that has stirred your heart. The harmonies were not complete until your mind, listening, helped shape them into experience. Think of the loved ones whose presence you have felt even across great distances. Perhaps that sense of connection is not sentimental illusion but a reflection of quantum entanglement reaching through the invisible web of reality itself. This is the invitation the quantum realm offers, to recognize yourself not as a fragment adrift in a cold and different universe, but as an expression of the cosmos becoming conscious of itself. You are a participant in the great computation, a spark of awareness through which the universe explores its own potential. And so, the next time you feel small beneath the stars, remember this: those stars are born in fusion fires governed by quantum tunneling. Their light travels across space as quantum particles until it strikes your eyes. Their ancient photons collapse into your experience only because you are here to receive them. The cosmos and your consciousness are entangled in a single, ongoing dance. As we reach the close of this journey, let us return to the rhythm with which we began. Take a deep breath. Feel your chest rise and fall. In this simple act, quantum processes are firing within your neurons, exchanging signals across entangled networks, turning raw sensation into experience. Every heartbeat is a quantum orchestra playing inside you. Every thought is a calculation unfolding across the informational fabric of existence. And perhaps, as you drift toward rest, you will carry this truth with you: reality is far more mysterious, far more beautiful, and far more participatory than we ever imagined. The boundaries between mind and matter, between observer and observed, between past and future, are not as sharp as they seem. You are not a passive traveler through this universe. You are one of its creators, weaving with every choice, every moment of awareness, every breath. The quantum realm is not far away. It is here, pulsing through you, inviting you to join the dance. So let yourself rest in that mystery. Let the questions remain open, like doors to possibilities not yet explored. Let the strangeness be a comfort, not a fear. For you are not separate from the cosmos. You are the cosmos, alive, aware, and endlessly creative. And as this journey pauses for now, may you sleep with the quiet wonder of knowing you are part of the universe's own awakening, a conscious note in the vast symphony of existence, dancing forever with the deepest mysteries of reality itself.